at you. What? I can't tell.
I didn't say anything.
I don't know. Okay, ready? Do I have bets in?
Yeah.
46.
Oh, it's
Didn't change. Why there's so many? It's because I never need to change them. We're gambling on well, not gambling, but we're seeing how many Chrome tabs I had open. Okay. Yes.
I paid for all
Look.
2 cores. I'm getting all of 2 cores.
Just because this computer will burst into flame in the middle of class doesn't mean that we can't put it out. Mikey's got a fire extinguisher back there, which I don't know if that'll be useful on a lithium polymer battery, but you know, we have it. Plus these are epoxy tables. Who cares if they burn to the ground? Okay. Afternoon, everybody. Today is another wonderful day of physics where we do indeed have the double period. Let's just quickly talk about this one. Nope. This one. Let's just quickly talk about rundown of the unit here. I was able to put up late yesterday, so it's sitting under Monday in the new unit of magnetism, the magnetism intergalactic. I have not split them yet on terms of like questions 1 to whatever, 4 to whatever, blah, 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 blah. But all of them are up. So if you ever did want to start looking at things, knowing that eventually I will assign them in their appropriate little things, you can. I need to do that later tonight. It's in the book of stuff to do. Yesterday, we talked about an introduction to magnetic fields, these Teslas, these B fields that are existing. And we talked about drawing them in some simple scenarios and how that you, too, can get lost in the Arctic if you don't know anything about Earth's magnetic field position. If you forget any of that or would like to see it, it's back there on Monday. Today, what we're going to do is we have a double, and today is an imperative day that we use our right hands, okay? That is the big thing for today. We're going to see a few equations here, but really today's big deal is this. Everybody do this. Noah, right hand. Right hand, Noah. We have a reason for right hands. Left hands are for galactic coordinate systems. We're not doing galactic coordinate systems. We're doing right hand rules, okay? So today, we're going to talk about right hand rules. Vector cross products, these are optional, okay? If you are going to go into an engineering or a technical field in college, I'd recommend watching that at some point in time, but we don't need to get into the nitty-gritty of cross product, vector mathematics and linear algebra. But it's there if you would like to see it, / you know where the video is when you get confused a year from now, okay? But what we are going to talk about today as well are Lorentz and Laplace forces, okay? So let's first bring us back into the world of mechanics, when things were safe and happy and not evil. Last year, when we studied mechanics and we studied forces, there was a period of time where you were looking at rotating forces. You were looking at forces that cause things to rotate. These were known as torques. These are torques, right? Torques are a vector, and these torques, as we saw last year, they are equal to R cross F. Do you remember that? Kyle is nodding his head. Thank you. Okay. If you're like, I don't remember this at all, please a refresher. Imagine this. Imagine Connor is looking at something, but Connor's nearest to the door, okay? Imagine that this is the hinge of a door. And this is the door itself. Where would you push on this door to open it easiest? Aiden?
Away from the hinge.
You push it away from the hinge. Now, when you say away from the hinge, what do you mean by that? Because I can interpret that.
It's farthest away from the door.
So you'd push out here.
Yes.
And like most doors, we do indeed put the handles far away from the hinge. It's a clever move, okay? Now, the only thing that I get a little bit worked up about in the Lord of the Rings is that hobbits put the handles on the center of the door. And it infuriates me because this is an unoptimal handle position. But they are very kind and docile creatures, so we'll leave them be. We will not burn the Shire to the ground. Now, if you are pushing the door open, you want to push with a force. And it is optimal that you push with this force 90 degrees from the object. If you try to instead pull the door off the handle like that, you're going to have a hard time. Maybe you're going to Hulk out and do it, but my odds are that you're not. Okay? We want to push often against the door like that. Even whenever you're holding a laundry basket in your hand and the door is beginning to open, what you tend to do is you tend to open it, kick it, and then as it's turning, you kind of butt it back that way. Everybody know the butt move, right? The reason why is whenever you do that, you're once again using your butt and you're going 90 degrees to it. It's the easiest way to open a door, okay? You know this intuitively. This is what it looks like from a physical perspective. Now, the reason why this matters is because this cross product down here really represents us taking R, which is that moment arm, a radial position. It is the distance you are away from the axis of rotation. We're multiplying it by F, and then we're taking the angle between this moment arm, this position vector, and the force itself. This is why it's so important that you open a door perpendicular to that door position, because if you're perpendicular, you get sine 90. And as our math classes have taught us, we know that sine 90 is a maximum of 1. Okay? That's what we want there. That's what we, in theory, saw last year a little bit, right? Yes? Right, Gio? How's the back rush treating you today? Excellent. Okay. Now, when we're looking at finding this angle of sine and when we're trying to determine the direction of the torque, here's how we do it. If we go back to our door example, here's our pivot. Here was the moment arm, R. It was the entire length of the door because we pushed at the edge. Even though our force vector was acting out at the edge, we will draw this force vector at the pivot. Because what we are not doing here is we are not creating a, well, there's a few ways to do this. I'll show you both ways to do it. We're going to put it at the pivot, okay? Just trust. Because we are rocking R cross F, here's what I'd like you to do. Using your right hand, take your fingers and place them along the first vector R. When I say fingers, you have 4 fingers. So take your 4 fingers and face them to the right along R. Just like that. Now, through the shortest angle possible, rotate these fingers to F. I could go all the way down. That's 270 degrees. Or I could much easierly go. See that? You're sticking out your thumb now, right? When you do this, the direction your thumb is pointing is the direction of the torque vector. That is the right-hand rule. Why don't you do this with your left hand, Noah? Because if you did this with your left hand and you went, your thumb would be pointing the wrong way. We use the right hand for this. That is our convention, okay? This means something. Who in here is a lefty? This means that our lefties are at a decided advantage throughout this little unit for us.
That's right.
The reason being is you're going to be rocking right-hand rules, and the lefties, they're going to be scribbling away and doing this at the same time. And you poor right-handed soul, you're going to have to write something. You're going to lose time here, dropping your pen, doing this, and picking it back up. That means if you're racing Michael Phelps, you might lose, okay? So if you're right-handed, you slam that down, you do this, you pick it back up. You got to do that. If you're left-handed, everybody knows lefties cheat, okay? It's a rule of law, okay? So that is one way to think about this. The other way to think about this in terms of, and this is the way I recommend. The other way, if you want to think about torque specifically, is if we did draw this as a force diagram and we put the force out here, this would rotate in a counterclockwise direction. And if it's rotating, you rotate your hand in that counterclockwise direction, your thumb's going to point out, okay? That works well for torques. In terms of what we're about to do, you can't see that as easily because we're not opening doors here. We're pushing charges around. So like I said, take the first force or the first vector here, R. Take the second vector, put it in the same position of that, and then through the smallest angle, one to the other. That's what we're going to be doing, okay? That is how you run the right-hand rule for a vector cross product, okay? This will take some practice to get used to. We will be fine. Questions regarding this? As I delete a million things that I have sitting in a file. Okay, give me half a second. My computer is, for some reason, my computer is going nuts. It may or may not have anything to do with the CPU being on fire. Work with me. Come on. Come on. Mr. Botzer fought hard to get you, computer. Don't let him down. I believe in you. Okay. So what we're going to be talking about here is using this idea of a right-hand rule to influence the direction of charged particles. One of the things we talked about yesterday was that if we have, and there's no way you can see that in the back zoom. If we have a charged particle moving through a B field, it is going to have a force acting upon it. The equation that dictates this is F equals Q V cross B. I'm going to rewrite this so it looks a little nicer in my opinion. F vector equals Q times the quantity V cross B. That's a big important equation. Burn that one into your retina. Don't actually burn it into your retina, but it wouldn't be a bad idea. Or it would be a bad idea. This is what we refer to as the Lorentz force. This is the force on a moving charge in a magnetic field. If you have a charge and it is moving within a B field, it is going to deflect due to this force. Okay? Now, this cross product here, remember, that's not a multiplication symbol. That's a cross product, okay? Your elementary teachers taught you wrong forever. Whenever they said that you multiply by putting an X, that was wrong. That's a vector cross product. When they then said, oh, use a dot to multiply, that is also wrong. That's the scalar dot product. That's whenever you did last year, like F dot D in order to do work, right? So they taught you wrong again. The only time you're actually multiplying is parentheses for life. Use your paranoia to your advantage, okay? So this X here is a cross product. It is the right-hand rule. And because it's a vector cross product, we get an output of a vector here, okay? So we're going to be able to see the direction of the force vector from this. Now, if you take moving charges and you stick them in a wire, we would call this a current. So if the charge movement is current through a wire of length L, we can rewrite that equation like this. And I'm going to write the equation here. It's going to be that a force equals a current times the cross product of L cross B. And this is a little weird because you don't think about like a length as having a vector, but currents cannot have a vector. Currents are just some value quantity. Lengths, though, can have a vector, and in order to get a cross product, we can only take the cross product of two vector quantities. Okay, so we have to write it like this. The length vector we're going to go in the direction of is in the direction of the current, but it is the actual length that we are taking that vector of. And we'll see that whenever we get into some of these examples here. Okay. From this equation, we can redefine the Tesla. I'm actually leaving that one to you as a part of the intergalactic. So, haha, next. And this is where we start getting into some fun today. Mikey, can you see that downtown? Okay. We're going to go through these uno at a time. What I have here is a positive charge with some downward acting velocity. It is in a B field, which is acting to the right. What I would like to know is, what is the direction of the force acting on this particle? So try it out. And Mikey, I was almost ready to come back here there, man. You were so close to getting the wrath of Reztob. Very good. Do not use your left hand. Try this. See what you get. Remember, for particles in a Lorentz force, you're using F equals QV cross B. V cross B will give you the direction of this force. So try it out. See what you get. You need to do this. You like physically need to do this. If I walk into a university lecture hall and it's exam time, I will see 600 crying students all doing this at the same time. It looks hilarious, but they will pass. Okay? It's called the right hand rule for a reason. Use your right hand. What's up, Aiden? Well, we'll see. Lucas, what do you think here for the first one? See that?
I have no idea.
You have no idea. How many people are on Lucas's page? We have no idea. Welcome to the right-hand rule. Here's how you do it. Remember, anytime we have a cross product, you take your fingers, and you go along the first vector. So for us, that is V. We then cross the fingers to the second vector. Okay, so you curl them around to the other one, which in this case is B. So everybody, either looking at your paper or at the board, doesn't matter, okay? Just reorient your body. Take your fingers, you got 4 of them, and stick them down. Now you need to get these to curl to the B vector. So you try that and we'll see what happens. This used to always drive me nuts. So what I would do, because I'm like, wait, do you want me to curl like this or like this? Because it looks pretty similar from my perspective. Redraw it. Your velocity is going down. Your B vector is going to the right. You need to curl your fingers this way. So velocity down, curl fingers to B. Your thumb is pointing out of the board. If you do this on a piece of paper in front of you, your fingers are like pointing towards yourself because they're down the sheet of paper. When you wrap your fingers to hit that B field, you'll find your thumbs going towards the ceiling, but it's coming out of your paper. Okay, so your force here is actually coming out of the page, which we know it as a dot. Remember how I said 3 dimensions are going to be very important for us? A cross product will result in something that is orthogonal, which is a fancy calculus term for saying perpendicular to everything else. If these are my first 2 vectors, V and B, this is V, I go V to B, and I get my thumb pointing out. Well, if I go out, notice how this is 90 degrees to here and 90 degrees to here. That is orthogonality. Even if these 2 aren't 90 degrees, if these 2 are like this will still be 90 degrees to each of them, okay? So that's what this cross product is creating for us. It's creating something, a new vector perpendicular to the other 2 vectors we had in this equation, okay? But it is weird the first time you do it, which is why everybody was on your team there, Lucas. Well, I don't know. So let's try again. There's vector, or the setup for B. Mikey, can you see that?
Yeah.
Just in case. This is a negative charge moving to the right with some velocity with a B field pointing out of the board. Hey. Elijah, you just did what I refer to as the chicken wing. Okay? Done it enough times. I got some arm pains now. I'm getting old. Physics is a taxing sport. What are my 2 possible answers here? Mikey? It could be up or down. Because of this orthogonality, if I have a velocity going to the right, that means my left and right directions have been taken. And if I have a B field coming out, that means my in and out directions have been taken. I can either go up or I can go down. I only have an up-down axis to play with anymore. So you immediately have a 50-50 chance of winning at this problem. So, fingers to the right. Now, I need to reach that B field, which is coming out of the board. So, boom. My thumb's going down. Okay? Play it again. Play it again. Velocity is going to the right. B field's coming out of the board. Notice how I stuck them together at the base where they both start? What direction does this velocity have to go to hit the B? Well, it's got to go like this. So it's got to close on that. That means my thumb's going to go down. Okay? If you do this on your sheet of paper in front of you, you'll have your fingers going right, but the B field coming out. You'll see you'll go down the page. So it'll kind of like your thumb's coming back into your body. Okay? So try that on your page as well. Make sure you're getting the same thing as we're doing at the board. Sometimes students can do it at the board because we like do it together. When they get on the paper, they're like stabbing themselves in the eye with the thumb because they can't figure it out. Okay, so make sure you can do it on both of them. We're just kind of moving things vertically and then sliding them underneath. Okay. So in this case, we had here and then out, and we got down for that, right? We all good on down? Awesome. Down's the wrong answer. Why? This is a negative charge. If we go back, and we go way back in time to when you learned about vectors last year. At about this time last year, you may have learned about vectors. If this is some vector A, if I want to draw the vector negative A, I go in the opposite direction, the same magnitude. So this is vector negative A. When we look at the Lorentz force equation, this V cross B will give us a direction based off of our thumb. But if my Q here is a negative quantity, then I need to go in the opposite direction of V cross B. I need to... Some heathens out there will tell you, oh, well, that means if you have electrons, you could just use your left hand. Out of here! Use your right hand and flip it. That way, you know you're always using the right-hand rule, and then you're just smart enough to say, it's an electron, it's negative, I understand how vectors work. Flip, and you're good. That way, you don't go into a problem, and you start going, oh, I could use my left hand, and then you're stuck using your left hand on a whole test, and you get the rest of the problems wrong, and you go insane, and you're like, Mr. Watson, why am I failing? And I'm like, because you messed up. I have had a student do an entire test before with their left hand. What do you want me to do? Tell them how to take their test? I say before the test starts, right hand rules, people. Right hand rules. If it's negative, though, you need to flip it. Okay? So we did the right hand rule, but we need to flip on this one. So we actually get that this answer for B is not down, but it is going up. Okay? Let's play again. Try it for C. This one, because we can see both of them, might be easier to redraw from the dot and then work from there. But just as a quick process of elimination, we immediately know our answers could be in or out. If the plane of the up, down, left, right are taken, we only have in or out left. Gio, talk to me, man.
So if the fielder is coming like towards you or away from you, your hand is oriented like this.
Yeah, your hand's either going to be like this to catch something going in, or like this to catch something coming out. And on a piece of paper, like if it was below me, this would be going into the page, and then this would be coming out of the page because I'm trying to grab the thing up here. Okay.
Can you repeat that?
So everybody do this. Look at the paper in front of you. Okay. Everybody stick your hand so that your velocity is going to the left. So our velocity is going to the left here. If my B field's going into the page, I need to wrap my fingers down because my B field's running away and I got to catch it real quick. Okay? If the B field's coming out of the page, I need to flip it and go grab it up here. Okay? Is that what you want to do? Okay, that's that idea for the pages. Okay, so just be careful of that. You can also think of it as if it's into the page, I need to attack my fingers into the page. If it's coming out, I need to release my fingers off the page. Okay. So I'm going to redraw this one. There's V. There's B. What's the angle between them? Numerically? 90, which is very nice for us because that means the sign of that cross product will be 1, so we could ignore it. And what direction do we think we've got here for our answer? So Ross, you're saying coming out? Well, if we go V to B, our thumb is pointing in, but it's negative. So we make the flip move, and we're coming out of the board. Okay, so we are coming out of the board. Our symbol for that, recall, is a dot. Look how messed up this is. My computer is on overdrive. Kyle, talk to me.
So you'd be like doing it on your paper, your thumb pointing away from you.
That is up. Like if I asked you, draw up on your paper right now. That's your thumb pointing away from you. That's up. Down is coming into your belly. There's your left. There's your right. Out of the plane is physically like out of your sheet of paper. It'd be like this. Into the plane is you're jamming your finger into the table. Okay? And that's why I say, like, we're doing these at the board, but, like, try them at your table. Because, like I said, some students can do it up here when we're together. And as soon as they, like, go down here, they're like, ah, and their brain explodes. And I got to scoop that up and put it into a mason jar. Okay? So make sure you're trying these in both places so you get an idea of, like, what this feels like. Some of them feel weird. Some of them, like Elijah had to do, like, you're going to chicken wing some of these. And you're going to be like, what the heck? Like, how do I get my arm to do that? Like, you got a bunch of pivot points here, people. Like, learn to use them. Learn the techniques. Thank you. Try D out. See where D takes you. Try it with the board. Try it on your paper. See if you get the same answer. You should. Velocity is going to the left, so my fingers go to the left. I need to get my fingers to attack that B field going in, so my fingers can hit that B field going in as I curl to it. That's what I want. My thumb is pointing down, okay? And if Kyle's working out on a sheet of paper, when he would have done that, he would have had a velocity to the left like this. His fingers would have hit his piece of paper, and his thumb would have pointed him right in the chest, and that's down the page, okay? So down is our answer here. How do we feel about these 1 to 5? 1 to 5. Play some games. What's the direction of the force vector?
The B foot going straight across.
Nah, it's coming a little bit down. No, what you thinking here? You think it's going into the page? What are you thinking, Gio? You think it's coming like up this way? Right?
I think it's going into the page rather than down the angle.
You think it's going into the page, but like kind of boring into the,
Yeah.
kind of like that. Other thoughts, comments, questions? Sir Ross?
Is this a positive charge?
It is a positive charge. Thank you for that clarification. Needed, right? Otherwise, they would have all given me the opposite of their answer. So yes, a positive charge. And for all of you at home, this is indeed a positive charge. You're saying just into the page? Gio?
It has to be perpendicular.
In order to maintain orthogonality, this force vector must be perpendicular to both. So, fingers along V, curl them to B, thumb is pointing into the page. We know we can't be up, down, left, or right because that's in the page. That's like in the plane of the page as well. And we already have our left, right. We already have some up and down due to the velocity vector. There's a component acting up. So it can't be this. It's either got to be in or out here. We know that it's not going to drill into a weird angle down like this because if it did, if it went at some weird angle down like this, then that's not going to be 90 degrees from one or even both of these vectors. The only way that we could do that is if we had this acting directly into the page, because now we could go 90 degrees and 90 degrees, okay? It's kind of weird looking at it 90 degrees, but if I twisted it like this, that's clearly 90 degrees right there, okay? So this is into the page right there for a positive charge, as Mr. Ross has clarified for us. So thank you for that, okay? This is in. Let's play again. Positive charge. Why make things more difficult? It feels a force acting up. What direction is the B field? Mikey, your thoughts on this?
The B field has to be going into the page.
You think the B field's going into the page? Lucas? You second the motion. The motion has been seconded. Do we have a vote? Because we clearly have a quorum. We can vote. All in favor of the B field going into the page? Aye. Uno, dos, tres, cuatro, 5, 6, 7. All opposed? You traditionally say nay at this point.
And
Very good. Very good. 1, 2, 3, 4. Abstain. Thank you for voting. And that means we didn't have roll call on the following people.
I said voting present.
Yes, right.
Well,
Present.
you,
A very common thing to do. You'll find out in a year. We've gone on a hiatus. If your velocity is to the right and you need to get a force going up, that means your thumb needs to be acting up. The only way to get that is if you curl to that B field going into the page. Now, technically speaking, if you want to get like real picky with this, you don't need to be all the way into the page. You could be like at some angle here as long as V is going into B like that. But if we do say like, hey, the velocity and B field are perpendicular, then it will be directly into the page like that. Okay, but it is some amount into the page to do this. Okay, so we're into the page here. That will give us a thumb going up, which is nice. Okay, take 3 minutes. When we come back, we'll play more games and get more headaches. Because we're not out yet. We're not out yet.
I think it was B. I don't remember. It was the one where the field's going out and going into the page. Yeah. Okay. So it's like it'd be like this, right?
Your velocity is this way,
Right.
but the field is pointing out. So get your fingers to go out. That's what you want. Because the B field, look, put your fingers this way because that's the direction the velocity is going. You need to get out.
Oh, so you're trying to bend them in the direction.
Trying to bend them in the direction that this
So
is
like
going.
for this one, so the velocity's going this way, and then we're trying to go.
You're trying to get the B field, which is going up. So how do you get V to B? Try again.
No, right. Like that.
Yes. Yes, absolutely.
Oh, wait, no. If you-
No. You're right. V to B is like this, but it's negative. So you flip.
Wouldn't that be X, the circle X then?
This would, if you did this, it'd be the circle X. But this is a negative charge, right?
Oh,
So flip.
opposite.
This is correct though. And then you flip.
Oh, yeah. Opposite.
This is right. You're doing this right. And that one's good for that.
And then D. Okay. So velocity's going this way, and it's coming towards me.
Or the B field's going into the board. B field's going into the board.
Oh, so okay, that confused me. I was like, okay,
Yeah.
so this is the B field my thumb, or is it just always this?
Velocity, and then you curl to the B field.
Okay.
You always curl to the second vector.
Okay.
You always curl to the
See,
second vector.
that's gonna confuse the heck.
Because it doesn't need to be a B field. There's many things that deal with this right-hand rule. The key is that fingers to the first vector, curl to the second, your thumb gives you the result. Okay? That is the key to it.
Pardon the interruption. Any junior or senior who signed up for the virtual college visit with you.
No touching!
University, please report to the
touching me.
Thank you.
Touching each other. I know how Newton's laws work. Crazy punks. Yeah. I need to put him. Oh, I can yell at a cloud. Ah! Old man yells at cloud.
You like Abraham Simpson?
Hmm?
You like Abraham Simpson?
Right? Good old Abe.
Abraham. That article. That's what I thought you were referencing.
Okay, everybody. We're back, and I've got more fun mind games to share. Positive charge to make Mr. Ross happy. Thank you. Velocity is going directly upwards. The B field is acting directly down.
And impossible.
It's really hard for me to tell if students like raising their hand to state something or if they're just like this. So I like Mikey's perspective of the left hand will be for I have a statement or question, because you know if I'm using my left hand, you're going to chop it off. Okay. Mikey, do you have a statement or question for us here? Okay.
So, you can't tell the direction of torque because in this case, it could be equal in any direction. Like, it could be equal in any direction along this plane.
Okay.
So would there would then be no torque force felt?
Well, we're not going to have a torque force here. So this will just be a force acting on a particle. Okay, it's not a torque in this case because it's not causing rotation around a pivot, but it's still the right-hand rule. So you're saying that you're claiming that there will be no force felt by this particle.
Yeah.
And Nate's agreeing with that.
double the force going up.
Geo, talk to me. You agreeing with that? What if I posit a different thought? There is no way to orient that you know for certain. And as a result, there will be an infinite amount of force. What do you think, Leo? Fishing out to you.
Looking at it.
That's my job. Leo, out of curiosity real quick, 'cause I'm on you right now. I've got you in my sights of my fishing line. I don't know how to fish. That makes sense. What's the equation that I'm basing all of this off of, Leo? Instead of calling that X, I'm going to call that cross. Okay, so V cross B. How could I rewrite this cross product? I'll give you a hint. V, B. Okay, yes, the Q goes in front. I forgot the Q. Thank you. And I'm missing a term. Now, when you open a door, what angle is so important? What's the best angle to open a door in terms of your force versus the moment arm? Say it again. If you're opening that door, which direction are you pushing? You're pushing directly perpendicular to it, right? What has a maximum at a perpendicular at 90 degrees? Take a guess. Like you're fishing for hope, Leo. I'm going to wait until you say something random. Pick a math thing that you know, because it's got to fit into this equation somewhere. Go with X. That is not what we're looking for. That's okay. What are we looking for, people? Looking for the sine of the angle. Looking for the sine of the angle there. Okay? If we go back up to the torque thingy, which, where did I even put that? Here. Remember when we did torques? It was RF sine of theta. Okay? And pushing that door and using the butt action gave us that 90 degrees to easily open the door because that theta was at 90. When we're down here with our charges, we technically have QVB times the sine of theta, where that angle theta is the angle that we're rolling our fingers through, okay? It's the smallest angle possible. Well, in this case, as Mikey pointed out, no matter how I put my fingers, my angle is 180. What's the sine of 180? It's 0. So the force is 0. Okay? So in this case, we don't have a force. If your charged particle is moving along a B field line, it will not experience a force. It can't. The angle is 180 degrees. Sine of 180 is 0. We see this via the right-hand rule because our right-hand rule breaks. It's like, what the heck's going on here? But when that happens, you should immediately go, oh, that's sine of 180, it's 0. We see the same effects when we have this setup. If you say, hey, look, here's our velocity. Here's our, whoops, let's make this blue. Here's our B field directly on top of it. What's the angle between those? 0. Sine of 0 is?
0.
So the force is 0. Okay? So we need to be careful about problems like that. Those ones can get a little confusing for us. Students forget them. They'll spend an hour and a half at like this, and then they'll just throw something at the wall. See if it sticks. Okay? Betty Spaghetti. How do we feel about the right-hand rule now on a scale of 1 to 5? Uno to 5-0. Do we feel a little bit better than before? The same as before, and it can't be worse than before because literally before we on part A, we had no idea what we were doing. Thank you, Mr. Ross. Okay. Hopefully, if you were online watching this, this video is up there, but we did a few extra little examples here to kind of give us some more insight as we were struggling there. Okay. Now we're going to use the right-hand rule again, but this time we're going to look at the force acting on a wire with a current running through it. So in the first example, I have a wire and the current is running to the right. In the second example, the current's running to the left. Now, please remember, because you have a current carrying wire, you're no longer using the Lorentz equation. You're using a Laplace equation for Laplace force. Very similar, but this time it's F equals I L cross B. As always, put your fingers in the direction of the first vector, which will be the direction of the current length in this. And then curl to the B field. Try this for A, try this for B, try it at the board, try it on your paper, make sure you get the same thing, and we'll talk about what you have found. Geo. In the left hand, like a heathen. Hold your answers momentarily. We will go through these ones together. I'm confident that you're going to do great. But we'll just burn these ones out together so we're on the same page. This is conventional current. So positive moving charges. Fingers along the direction of current. My B field's going up. So I curl those fingers up. My thumb points out of the page. So for this first one, I see I'm coming out of the page as my answer. For the second one, B field going to the left, or excuse me, current going to the left, B field going into the board, thumb shall point down. Now, Gio, your question there, whenever you talked about, like, are these currents positive? We will always use conventional currents here. So when we have this equation, we no longer have to worry about, like, negative flipping. Okay, that is purely for the negative electron charge that we see with the Lorentz force. Okay, for Laplacian equations, we always think about currents as positive charges moving. And if we did think about positive charges moving left, that would be like V cross B, and we'd get down anyways. Okay. So this equation does derive from the fact that we think about charges moving, and we use that right-hand rule to solve them. How do we do on these two, A and B? Good. 2 for 2, 1 for 2, 0 for 2. Okay, cool beans, cool beans, cool beans. You will get super good at the right-hand rule. Okay. the reason why you'll get super good at the right-hand rule, well, one, you need to, and two, the big cheese is coming to town. Okay? And this year, the big cheese has gone digital. What? This is a big deal because the big cheese is like 28 pages thick. And I used to print them all out. And that's like 28 front and back. So, woo! So it's on all digital this year, which is pretty awesome for us. Okay? Before we go on, though, any questions regarding these right-hand rules and what we're looking at? Okay. I have it sitting on Thursday because what we will spend Thursday doing is the big cheese. But if you feel that you could use some more reinforcement and some more cheese in your life, if you go to the big cheese, there's a little intro on it, and it says go here. It'll take you to this amazing webpage. Shazam! With some right-hand rule topics, okay? Some of these you can do. This one, I haven't taught you yet. So, skip it. This one you can do, though. You have a wire in between two magnets. This is the direction inward on the page of the force. What direction is the current flowing? Okay? There are 41 of these. They cover pretty much everything under the sun. But there are some that you cannot do. Right now, any of those solenoid things with the wires wrapping like that, you don't know. They're super easy. They haven't taught you yet. Okay? Anytime you see a square of wire in a B field, you don't know those ones either. Okay? So don't worry about those ones. This, you know that one. This, you know that one. You can work this one out. You can work this one out. You know that. You know that. You know that. Okay? Some of these you'll have, some of these you won't. But there's 41 of them. You want to be able to just crush these 41 in like 23 minutes. That'll be a good time. Okay? Because literally when you see a right-hand rule, beyond this class, those are easy points. Because you're literally going, I'm going to drop my pencil or keep it because you are a lefty, and you just go, whoop, whoop, yay, and you're done. Okay? It's the beauty of the right-hand rule. What we're going to talk about, though, before the end of this class, is we need to talk about another right-hand rule that exists. Because there's so many of them. Okay? Imagine that I have a wire of current I. And this current is acting to the right. I know that not only will a moving charge in a B field feel a force, but I know that a moving charge will create a B field, which means that this current here is creating a B field. What is the direction of that B field? Anybody want to posit a guess? You can guess a lot of different things. And if you're right, you will be a hero. Gio, random guess. This current is acting to the right. This current, because they're moving charges, will generate a B field. What direction do you think the B field will be pointing? I have an out of the page. Up. I have an up. Geo?
Does it go, like, back there?
You're saying like,
Go that way, go across, and then it moves back.
like our bar magnet?
Yes.
A wonderful guess. Down? Other guesses? Mikey?
Left.
Left. Mariah, your random guess of the day?
I like Geo's.
Geo's idea. I think Geo's idea is very neat. Oh, you're all wrong at this point, but Geo's closest. So I say guess randomly. You never know what you're going to hit. Geo's still better.
Does it just go, does it just follow the same path and go?
Nope. Nathan?
We'll just completely just follow through.
Like going like this?
Yes.
No, I think that was Geo's last statement.
Oh.
But no, we'll not do that. Here's the right-hand rule for designating a B field due to a current of wire. Thumbs, activate. Take your thumb and point it in the direction of the current. Then do this with your fingers. Your fingers are the B field. Your fingers are the B field. This means the following. Above the wire, your fingers are coming out of the page. So if you guessed out of the page, you're feeling pretty good right now. Except when you go below the wire, your fingers are going in. And if I do this all the time, I take a pen or a pencil and I put my thumb along that so I can be above it and I can be below it. Okay, you'll see students do this all the time. Very common strategy. I'm above the current, I'm below the current, so you can see my fingers are going in below it. So below it, I am in. With this in mind, how is this B field acting? Mikey? It's just in a circle. It's actually not going to like helix forward. We actually think about it as, you know, there is a B field like this all around the wire. I'm not going to draw that, a helix. This is the B field. It's actually looping in a circle around our wire here, okay? And we use this right-hand rule with the thumb along the wire and then curling our fingers in order to get this, okay? So it's a little weird, but that's what's going down. This does mean that if we want to write things above or below, this is coming out, this is going in. What would the B field be right here? Here in space.
Starting to come down.
Here in space, my fingers are acting down. If I take a tangent line from that circle, I'm going down out here. So out here in space, I'm going down. Behind the wire, then, I'm going up. Okay, we can envision like a circle kind of going around this. Okay, so that's what's going on there. It's very weird to think about, but that is what's going on. Okay, and that is our right-hand rule for a current-carrying wire to figure out the direction of that B field. So now you can ask mean questions like this. Here's a current-carrying wire. A positive charge moves with a velocity towards it. What direction is the force going to act? Thoughts, Aiden?
I think if we're making this the current and we're going to make this the velocity, make this velocity, then it's going to go all the way to the right. But I think it's going to do like we did in the last one. It's going to loop back around instead of go left.
I'm looking for the force here.
Oh, force.
I want the force on that charged particle. I want the force on that positive charge. So I would agree with you here. I would agree with you in that the B field is going to go in here and out here. What's that mean our force is going to do? Lodge, what do you think on this one? The B field's going, as we've drawn in blue, and the positive charge is coming to the left. Pull out your hand. That's how we do everything. Fingers left. And then which way is the B field going? In or out? So if we're rocking in, attack the board, your thumbs are pointing down. So our force in this case is actually down. This is a common AP question because in one question I asked you about 2 right-hand rules. And if I made it a negative charge, then I would have technically asked you about 3 different topics in one question. Do you know how to make B fields from current carrying wires? Can you do a right-hand rule? And do you understand the idea of a negative charge causing that right-hand rule to flip? Yay! Like I said, you're going to do a lot of these, and you're going to get really good at them. Okay? But this is a very important thing in this unit. It's a very important thing. What's up, Aiden?
How come the force would be going upwards? Are we going? Because the way you set it up, or at least the way that you drew it, because of my explanation, you're having it come this direction, and then you're having it come back around. So wouldn't that mean that the? So
what I'm having loop around here, like this, and notice I don't draw this back edge of it here because that's behind the wire. This is the B field.
Mm-hmm.
So on this right-hand side in the plane of the board, this B field's like going into the board right here. If the B field's going into the board here and the velocity is coming to the right, in order to find the force, I care about V cross B. So I go V cross B, and that gives me a thumb going down. Because I need to use this equation. I need to use the F equals Q V cross B to do that one. Okay? So even though I did have to get this B field over here by using that right-hand rule, I then needed to use a second right-hand rule to get the force vector. So common little things that pop up in the world of physics. Okay? How you doing, Leo? Awesome. Mr. Bosser, my brain is mush now. Wunderbar. Okay. I don't want to get into looking at circular motion due to charged particles in B fields until tomorrow's single period. We still have about, what is this? 14 minutes of class left, I guess. So if we would like, we could begin and get out of the way here some of these intergalactic problems. Like I said, I put these up on the canvas. The first 4 go together. They're just basic things from yesterday. Here's the breaking down the Tesla into more common SI units that I said I wouldn't do in the notes because it was yours for an intergalactic problem. There it is. And then here are just drawing B fields and then recognizing what's going on with these domains of the object. Okay. We can't really go on to 6, 7, 8, 9, 10, 11, 12 yet. But if you wanted to start those first 4, and then if you did want to start jumping into big cheese to try to get yourself a little bit of practice with that, that's how we'll spend the rest of this day right here. Sound good? Sound like a plan? Any feedback is nice.
Yeah.
Excellent. Excellent. Mikey, can you see this, or are you using your own Chromebook to look at this?
Oh, I can see it. I just looked at my.
I don't know. I don't know what people are doing at this point. Oh, it looks like a lot of people have open Chromebooks. I like blink for a second and everything flips up.
I can see it from here.
I'm gonna keep it just like that for a minute. Yeah, that's what I thought. Leo, you good? Can you see that? No, can you see that? And like I said, these are also in the Canvas modules for that. For all of you who are out there in that world. I'm sorry, you guys can't see this now. I'm going to flip them over to this. This is just what we're looking at here. Miss Caruso Day. Any idea where's that from? Huh? Yeah.
I swear I saw him. I don't know. I don't have context. I might not have.
Yes, you're suspect to see anything today.
Yeah.
Okay, yeah, he just wasn't here today. That's okay.
Oh, no. I saw a ginger that kind of looked like him, but wasn't Lucas, so I assumed. Kidding. Ginger.
Okay, if you're out there watching the stream right now, I'm actually going to close it so that it will generate a file for me. And I'm going to upload this entire file into the Canvas so that if you want, you can watch the old videos that I've like actually gone through and done the lecture. And if you want, you can see this entire class lecture again where we do those extra examples. Okay, so goodbye. We're just working on the intergalactic for the rest of class here. Just these first four, and then the big cheese if you want to spend some extra time doing that. Okay, so ta-ta. I need to close this out somehow. How do I do that?